We started section 3.1 last time, simple rate of change formulas. And we had discovered a few different rules so far. So let me just flip through where we had our properties. Rule number 1 was that when we had a constant, which is just a number, and we take the derivative, we get 0. It's a great rule. Rule number 2, when you have a linear function, a line, the derivative is just the slope of that line. Or you can think of it as being just the coefficient in front of the variable x. When we have a power rule, and I didn't mention it last time, although it is true that that power can be anything. The power could be a fraction. It could be a decimal. That power could be pi. Do you know pi is a number, right? It could be pi. That power could be a radical 2. It doesn't matter what that exponent is. With one exception, the exponent can't be 1. That's not true. The exponent can't be 0. That's what I want to say. Okay, the exponent can't be 0 for this to work. We'll get to what happens when that happens later. It's actually in 3.2, but it can't be 0. But the exponent could be anything else. Radicals, decimals, fractions, all kinds of stuff. Okay, and the property still works. You bring the exponent down in front, and you decrease the exponent by 1. And we left off, I think this was our last one. Is that true? Yeah, we haven't done this one yet. This is our last one that we did last time. And it talked about what happens when we have a constant in front of a property, whatever it is. And we basically learned, though I didn't phrase it that way, that the constant just comes along for the ride. You take the derivative of whatever function you have, and then the constant just gets multiplied by what you had before. So you have k times f prime of x. All right, we have one more rule. This is actually called the sum and difference rule. There's only one of these that we haven't done, and it is problem number 9. So we're going to do problem number 9 out, and then we'll write in 10 and 11, which we've done before. So on problem number 9, the first step is to do, there are functions called c, so c of x plus h. So we have negative 6 times x plus h squared plus 7. So x plus h squared is x squared plus 2xh plus h squared, and then plus my 7. And we'll distribute our negative 6 through, so negative 6x squared minus 12xh minus 6h squared plus 7. Step 2 is to take that c of x plus h and subtract off c of x. I'm going to shortcut this. I think Jacob was the one asking me about shortcutting on something he had done. I'm going to shortcut it the way that you described. So we know that we're subtracting off, in this case, the 6x squared and the 7. I'm run out of space. So we're going to eliminate those. It'd be all the other pieces that remain. So that would include my negative 12xh and my negative 6h squared if I eliminated the other pieces. Okay, normally I show that out more fully, but I'm running out of space. So I'm just subtracting off the pieces that are in c of x. 3 is to divide by h. So I have negative 12xh minus 6h squared. We'll divide by h. So we eliminate this h, one of these h's, and that one. And that leaves me with 12x. I'm out of space at all. That's not going to work. Negative 12x and negative 6h. Step 4, my limit as h goes to 0. You guys have so much more space. I need to reorganize these slides. Of negative 12x minus 6h would be negative 12x. So, up here, c prime of x is negative 12x. Okay? All right. The other two, 10 and 11, we've actually already done them before. On number 10, we actually did this one and we found out that it was 3x squared minus 5. And on number 11, we found out that this was negative 4x plus 3. Those were from previous work that we had done. So using these above rules, I didn't mean rules, using these above problems, the idea would be to try and figure out what is the general rule that you see here. So every single one of these problems has two different pieces added together, right? What happens when you take the derivative of something with pieces added together? What's it look like? You're exactly right. It looks like we've combined rules we used earlier, right? And so we are building upon the rules we used earlier as we move through these properties. That's definitely a true statement. And in fact, what you see happening is, I'll use just my last example here, number 11, that when you look at the negative 2x squared, and you see that the derivative is negative 4x right underneath it, and then you look at the 3x, so that's the power rule, and then you look at the 3x, you see that the derivative is 3 underneath it. That's the linear rule. We're combining the rules from before. But more specifically, what we're doing is we're actually sort of doing it one piece at a time, right? And you might be looking at it and thinking, well, how else would we do it? And it's not necessarily a foredrawn conclusion that that's how it should be done. Feels like it, but we'll encounter something in section 3.6 that shows that that doesn't always think, what we think does not always work out like that. It does here. It seems very natural and it seems very logical that when we're taking the derivative of two pieces that are being added or subtracted actually, that we would just take the derivative of each piece individually and then add or subtract their results. And that's what this property says. The property basically says that what you expect to happen, happens. We just work with each of the pieces individually with whatever rules that we had from before. We're about to have more rules in 3.2, and we combine them with the addition or subtraction that they're already combined with. Okay? There is one additional fact that I want you to recall, not because it's anything to do with calculus, but because it's an algebra fact that comes up in the middle of your calculus. And it has to do with exponents that are in denominators and in radicals. So this first one, when I have 1 over x to the n, that is the same thing as x to the negative n. Okay? So if you have a simple x to a power in a denominator, you can move it on up and just make the exponent negative. It's very valuable because that actually makes it look like a power rule then, when it previously looked like a denominator. Okay? The other one here, where there's radicals, you'll notice that we didn't have any properties that said, hey, what do I do with radicals? And in fact, no such properties exist. And the reason they don't is because they're encompassed in all the other rules that we have to use more generally. So in particular, this radical can be rewritten in exponential form as x to the m over n. So it stays x to the m, and then the index becomes the denominator of the exponent. Okay? And again, what that does is it puts it into a form now that looks like a power rule. So we could actually use the power rule on either one of these from this point. We take the number down, decrease the exponent, all that stuff. Okay? So that's what's happening here. So in your homework for 3.1, you are not doing what I did in the homework or in this lesson. You're not using limit definition rules. You're using these properties. Okay? So I actually kind of like it that we didn't finish 3.1 because you'll see how it all plays together a little bit better after we do 3.2. So I'm going to pause this section and we'll move to the other section.